Welcome to Module 16 of the Six Sigma Institute's Lean Six Sigma Certification Curriculum, which follows both the Council for Six Sigma Certification and the International Association for Six Sigma Certification bodies of knowledge. A full copy of the Council for Six Sigma Certification's Book of Knowledge can be downloaded from the course description section for free. In this module, we will be discussing the control phase of the DMAC methodology. This module will take approximately 60 minutes to complete, and at the end of this module there will be a 5-question quiz on the topics discussed, which you can complete on your own at any time. You will also find several Six Sigma tools that you can download, including a control chart template and a statistical process control template, both of which are Excel files. During the control phase, teams build monitors that let them ensure that the process continues to work successfully after changes are implemented across the regular business process. In this section, we will discuss the setting up of controls. We will cover the importance of revising the failure mode and effect analysis and recalculating the risk priority number, as well as the creation of a control plan and the use of visual management to enforce and maintain control over the process. At this time, Six Sigma teams might want to revisit the failure modes and effect analysis. We previously discussed how the tool listed potential failure points and ranked them according to severity, occurrence, and detection, calculating a total risk priority number. At the beginning of the control phase, teams should revisit the failure modes and effect analysis and note what recommended actions were completed and recalculate the risk priority numbers for the improved process. In revisiting this tool, the team is able to see that positive and significant changes have occurred because of the solutions adapted during the improved phase, and an update to the tool will help the team identify the next problem or root cause that might be addressed. Remember, Six Sigma is a continuous improvement initiative. The team might have implemented a solution and met an improvement goal, but further improvements can always be made. Control is a time to review the process and suggest possible improvements for future projects. To facilitate continued success, Six Sigma teams should create a written control plan for the process owner. The purpose of a control plan is to help the process owner and business team track and respond to key performance indicators so that the process remains improved. The control plan should be concise, easy to reference document that tells the business team when to monitor, how to monitor, what range of data is acceptable to the monitor, and how to respond with corrective action if the range measured is not acceptable. Control plans can be spreadsheets, specialized digital documents, or hard copy documents posted at a workstation. In creating a control plan, we need to include certain pieces of information, such as the company, division, or department name, the name of the person who created the plan, the date the plan was created, the name of the person who last edited the plan, the date the plan was last edited, as well as the project and/or process name or identifier. Because of the complexity of a control plan and its importance to maintaining control over the improved process, we need more information such as the process owner, a list of process steps where control action is required, the critical to quality or metric associated with each action required by the plan, the limit specifications or the acceptable range of measurements, the unit of measurement, and the method of measurement that should be used to gauge the product or process being controlled. To ensure that bias in the control process is limited, we need to indicate the necessary sample size and how often the operator should be performing the measurement. We also need to know who is responsible for that measurement. Is it the machine operator, a member of the quality team, or even a manager? The chart needs to identify where the information needs to be recorded whenever it is collected And in the event that an issue is discovered at the time of the measurement, what corrective actions are necessary to bring the process back under control. The control plan should also identify and associate policy and procedure documents that the organization may have with regards to the process. In addition to providing a control plan, Six Sigma teams can implement specific visual controls in a workplace to help business teams maintain a controlled process. We covered some of these tools previously when we discussed lean process management, such as the 5S's. Other visual controls teams might implement include signs, posted matrices and instructions, auditing boards that let teams keep track of individual or group performance over time, color coding, and safety signals. Standard operating procedures can often be distilled to visual representations on posters. Other visualizations might include safety procedures in a medical environment, such as visual reminders for hand washing and short pictorial presentations for how to operate equipment, such as hospital beds. In an office environment, pictorial instructions are found on copy machines, where pictures indicate how paper should be loaded, and visual GIFs are often displayed on LED screens to help employees remove jammed paper. One of the most common methods Six Sigma teams use to monitor a process is the control chart. A number of types of control charts exist, and Six Sigma experts must choose the right control chart for the type of data and analytical purpose. In this section, we will discuss the statistical process control chart, including the basic chart elements, as well as the 8 Nelson rules. We will also talk about control versus capability and explain what the sigma level has to do with it all. The basic control chart has not changed much since it was first introduced by Schuhart a century ago. It is, in all simplicity, a line chart of data with plot points for specific data points. There will be an X-bar line which represents the average of the data points. Above and below the X-bar line, there will be two more sets of lines indicating 1 and 2 deviations away from the average. Beyond these lines are the upper and lower control limits, which are located at 3 standard deviations from the average. Generally speaking, we want all of our data points to fall within the upper and lower control limits, and it is obviously preferred that these points stay well within the 1 standard deviation lines. But this is not always possible in a real-world scenario, which is why we use the 8 Nelson rules to read the control chart. The Nelson rules are a method in process control of determining whether some measured variable is out of control. The rules for detecting out of control or non-random conditions were first postulated by Schuhart back in the 1920s. But it wasn't until 1984 that the Nelson rules were first published in the Journal of Quality Technology by Lloyd Nelson. The rules are applied to a control chart on which the magnitude of some variable is plotted against time. The rules are based on the mean value and the standard deviation of the samples. They are used to identify an out-of-control process and are based on the points of data on the control chart. The test may indicate a potential issue depending on how many points, where they are located, and what they appear to be doing. They may also point to what may be causing the actual problem. Rule 1. A single point on the control chart appears outside of the upper or lower control limits. If this occurs, process owners should take immediate action, because it is evidence of a major problem within a process. While there is a very remote possibility that shifts outside of 3 standard deviations can occur randomly, the likelihood is only 3 out of 1,000. If you take a look at the chart, you will see that the third data point extends above the upper control limit, and that the 7th data point extends below the lower control limit. Rule 2. 9 points in a row appear on one side of the center line. This indicates that a change occurred in the process. If the process owner knows what change caused the shift and it was an intentional change, then nothing needs to be done and the control chart will write itself over time with the new data. Otherwise, the process owner should investigate the process. If you take a look at the chart, you will see that the 4th through 12th data points are all located above the X bar or average line. Rule 3. 6 points on the control chart increase or decrease in a row, indicating the process is becoming less or more efficient or is generating fewer or more errors. Process owners should investigate unless there is a known reason for the trend. If you take a look at the chart, you will see that the 6th through 11th data points start more than one standard deviation below the X bar and incrementally increase until it extends more than two standard deviations above the X bar line. Rule 4. 14 points on the control chart in a row alternate moving up and down. This could indicate variation in machines, employees, shifts, or overcorrection. If you take a look at the chart, you will see that rather than a continuous rolling set of data points along the X bar line, we have one high, then one low, then back up, then back down again, alternating back and forth along the X bar line. Rule 5. 2 out of 3 points in a row on the control chart are in the upper A section or in the lower A section. This might indicate some type of special cause creating sudden high variation. If you take a look at the chart, you will see that back to back, the 7th and 8th data points both extend more than two standard deviations above the X bar line. Rule 6. 4 out of 5 points in a row on the control chart are located in the upper or lower B section or beyond. This can indicate a problem of major causation or a shift problem similar to that of test 4. If you take a look at the chart, you will see that back to back, the 8th through 11th data points all extend more than one standard deviation below the X bar line. Rule 7. 15 points in a row are located within the C section above or below the center line. This can indicate that control limits are no longer relevant to the process. If a team has improved variation of a process, they should recalculate control limits to new parameters. Alternatively, this might occur temporarily when short-term variation is high or low relative to the rest of the points on a control chart. Now, if you take a look at the chart, you will see that all of the data points are tightly located well within one standard deviation above or below the X bar line, and there are no points that extend into or beyond the one standard deviation line in any direction. You may think that this is good, but there should always be inherent variation in any process. And finally, Rule 8. 8 points in a row on the control chart are located on either side of the center line, but none are located in the C section above or below the line. This could indicate an issue of mixed resources or processes. A team might think that they are measuring a single process when they are actually measuring two processes, for example. Alternatively, it could indicate a major difference in processing for two employees or teams. Now, if you take a look at the chart, you will see that the 4th and 5th data points extend well beyond one standard deviation above the X bar line. The 6th and 7th extend below one standard deviation, then the 8th and 9th extend above, with the 10th below and the 11th above. It's important to note the distinction between a controlled process and one that is capable of meeting customer requirements. Controlled processes don't have a lot of variation. Capable processes don't have a lot of variation, and the outputs center around a customer requirement. This is why both control limits and specification limits are important. Consider the example used in the book about sugar in the chocolate mix. The specification limits ranged from 4.9 to 5.1 cups of sugar in each batch. It is possible for a control chart to show that the process is in control if the measurements range from 3.5 to 3.6 cups of sugar per batch. But the process owner should know that those measurements aren't going to contribute to a product that meets critical to customer quality requirements. To understand how a process is performing against specification limits, Six Sigma teams can calculate sigma level and process capability. The sigma level is the number of standard deviations between the current process center, as measured by the median, and the nearest specification limit, not the control limit. The equation for sigma level can be seen here, and you would choose the one which is closer to the median. For example, if a process has an upper specification limit of 5 and a lower specification limit of 3, a standard deviation of 2.5, and a median of 4.2, then you would calculate from the upper specification limit since the median is closer to the upper specification limit. The process capability is calculated by dividing the sigma level by 3. Process capability is denoted as CPK. A process capability of 1.33 is equal to a sigma level of 4, which is what most experts agree is the minimal level at which most customers will be satisfied. Under statistical process control, many organizations aim for a process capability of 2.0 with a minimal acceptable process capability at 1.5. After we have completed the control phase and the improved process is up and running, it is time for the last tollgate. By the time your team gets to this point, you will already have calculated the performance and capability of the new process. The team will have written a control plan and communicated it to the process owner. A monitor would have been created for the process, either through procedures for manual data collection or automated generation of control charts. The team will have provided the process owner and business team with all of the tools and information required in order to maintain the improvements. As with the completion of every phase, the sponsor or champion must be informed about the state of the improvements and sign off on the project's completion. And after all of this is done, the team should meet to celebrate the project's completion, reflect on the project, and generate a list of ideas for future improvements. The team has calculated the control and specification levels based on the data. They have also identified the voice of the customer and the voice of the product levels, which allow them to calculate the overall performance and capability of the newly improved process. A control plan for the newly improved process has been created. If the organization already has a template, then the team simply fills out the control plan. But if there is no template, then the team should create one that can be used for all of the processes within the organization. If more than one change was created or more than one process was improved, then the team will need to make a control chart for all of them. These are then numbered with their first version number. Anytime that a plan is updated, the information is changed and a new version number is added, the old plans are still kept in the records of the organization as part of the organization's living standard operating procedures. A monitor and response plan will be needed for the newly improved process. The team will need to identify the parts of the process to measure and define the acceptable measurements and their precision. A frequency for the measurements must be set, and those who will handle the measurements will need to be identified. All of this will need to be properly documented with the project records and integrated into the standard operating procedures. The process owner will be taken over the newly improved process, and it is the Six Sigma team's responsibility to ensure that the owner has the tools and info needed to operate the process and keep it in control. The team will need to identify what tools are needed to monitor and control the process. If those tools are already available, then the team will need to provide them to the process owner. But in the event that the tools are not already available, then the team will need to create them and then provide them to the process owner. The team will also need to train process owners how to use the tools and how to implement the controls. The tools and training provided need to be properly documented in the project records and integrated into the standard operating procedures. As always, the sponsor or champion must be informed of the progress and must sign off on the project completion. To do this, the results of the improvement phase are compiled and presented to the sponsor or champion. The team presents the control methods and shows that they have been put into place. The team will need to confirm that the standard operating procedures have been updated with the newly improved process and that the training manuals are updated as well. Since it is best to end the project with a small celebration and a recognition of the team's efforts, the sponsor or champion should be informed of the celebration and invited to participate in the recognition process. When Six Sigma teams deem improvements and the related process to be capable and in control, and they have passed those processes back to the business and process owner control, they should take the time to celebrate and reflect on the outcome of the project. This is usually done following the final Tollgate review with a sponsor or champion, and can be a quick meeting to close loose ends, recognize the work done by the team, and discuss lessons learned within the process. The celebration and reflection meeting is also a great time for team members to bring up ideas for possible improvement projects. While improvements and the related problems and causes are still fresh on the team's mind, they can effectively brainstorm ideas for the next steps. As with any brainstorming session, no idea should be automatically held off the table because it seems silly, would be too hard to implement, is too costly, or seems too big. Not all of the ideas will become future projects, but the team's input provides valuable information that the Black Belt can later share with Six Sigma leadership panels. Throughout the project, the team has been tempted with one idea after another that would lead to scope creep. But the leader has paid close attention to the goals and targets of the project, and whenever ideas come up that are beyond the project scope, they were written down and saved for later. It is at the end of the control phase, as the project winds to a close, that it is time to revisit these lists with the team and prioritize them. The team leaders, champions, and sponsors can use this list as they plan for the implementation of future projects, because in a continuous improvement business culture, we never stop making improvements to the process.